Hello everyone, welcome to Calculus Chapter 8, Lesson 8.1, Equations of Lines in R2 and R3, also known as 2-space and 3-space. So recall, in grade 9 you would have seen something like this, not maybe in that form. This is the equation of a straight line in standard form. And now, if I was to do a little bit of rearranging, I can easily show that that equation is the same as y is equal to 1/2 x plus 5. This is your slope-intercept form, whereas the original, that's your standard form. Now, what both of these forms have in common is that they are both scalar forms. Today, we're going to be looking at vector equations of lines. All right. So let's take a look at what this line looks like anyways. So from this, I can see that it has a positive slope and it has a positive y-intercept. So mainly what I'm going to be worried with here are the top two quadrants. So there's y and there's x. Okay, I know my y-intercept is 5, so I'm going to go 5 units up here. So that's 4, 3, 2, 1. And I'll go 1, 2, 3, 4, 5 units here. 1, 2, 3, minus 3 on that side. There's my 0. Okay, so my line, like I said, it has y-intercept of 5. And it has a slope of 1/2. I'm just doing a rough sketch here. You don't have to be exact, but it has a positive, somewhat shallow slope. So there's your line. Okay. The whole point of doing this is to show you how we are going to try to get to vector form. Regardless, a line is a line. It looks like this. The way you describe it depends on whether you describe it using a scalar equation, which then you can break down into two different forms, or a vector equation. Now, in order to understand how the vector equation works, you have to remember how we add vectors. So what I always want to do is make sure that I'm starting from the origin. I have to be able to get to any point on this line. After all, that's what these equations do. If I plug in any value for x, I can extract any value for y. So I can figure out any point on this line simply by using the equation. Likewise, using the vector equation, I should also be able to arrive at any point on the line. Now, first things first, to get to any point on the line, I first have to get to the line. And this is what's really unique. When you have scalar equations, this is the only scalar equation that can model this line. But there are infinitely many vector equations that can model a line, assuming that it has an open domain. Okay, so there are infinitely many vector equations for straight lines, and there's only one scalar equation of a straight line. Okay, so the reason is, well, I was just saying, to get to any point on the line, first you have to get to the line, right? So let's say I want to know what this point is right here. Well, I have to get to the line first. So maybe I get to the line here, or maybe I get to the line here, or maybe I get to the line here. So that means I need to know some point on the line first. Maybe it's not the point that I really care about, but I have to get to the line first. So wherever I decide. So let's say that I am given this point on the line. I know it. If I know that point on the line, then I can construct a position vector starting from the origin going to that point. Okay, so now I'm on the line. Think of it like this. You're on one island, and this is another island. You have to get to the other island first before you can start traveling along and looking for food. So we're going to call this here R0. Hopefully you can see that on the camera. That's R with a subscript 0 and the vector symbol on top. Now, I have to be able to move up and down the line. The scalar equivalent of being able to move up and down the line is given by the slope. That tells me how much I move to the right and how much I move up or down and to the left, or any combination of those. So maybe I have something that allows me to move up this line. I might also have a vector that allows me to move down the line, but for this thing, which is called the direction vector, I either move up or down the line. So there's only really two main types of those you can use. And then, of course, you can use any scalar multiple of those. So M is something called the direction vector. That is a vector. It can be this long. It can be a little longer, as long as it has the same slope as the line. And it can even go down the line. All right, so if I was trying to get to that point, now all of a sudden I have a way to do that. if I remember how to add vectors, and I add vectors by adding them tip to tail, so these two vectors are already tip to tail, that means the resultant, the sum of those two vectors, I draw from the tail of the first vector to the tip of the final vector. All right, so this is going to be my resultant. So I'm just going to call that R. Okay, so R is what starts from the origin and it gets me to any point on the line. Now, if I manipulate M, so if I take some scalar multiple of it, then that means I can actually move up and down the line. Okay, so in this particular case, so remember, I already know the equation of the straight line. I know what the slope is. In this particular case, my M is a vector after all, so it's going to have an x coordinate and it's going to have a y coordinate. Okay, so think about it like this. M is allowing me to move along the line, so that means it has to be moving in a certain direction with the x, certain direction with the y. It's moving right with the x and up with the y. And if I look at my slope here, so my slope is 1/2. Okay, so notice the letters are even the same. The 1 on top, that's the rise, and that affects the y values. And the 2, that's the run, that affects the x values. And so for every 2 spaces I move right, I move 1 space up. Okay, so with a vector, I know that my x quantity goes first, so x is 2 and y is 1. So my direction vector is 2, 1. Now let's say I know a point on the line. Okay, so you can easily figure out a point on the line, or based on even this equation, or maybe the question gives it to you. If I know a point on the line is, let's say, 2, 6. Remember, I'm using round brackets for points and square brackets for vectors. If a point on the line is 2, 6, then a position vector, remember position vector means it's a vector starting from the origin, then a position vector going to this point is 2, 6, but in square brackets. Okay, so that's what allows me to, again, get to the line. So overall, what I'm trying to show you here is that this vector R is given by a combination of R0 plus, and not just M, it can be any scalar multiple of M. So T is an element of the real numbers. It can be positive, negative, decimal, whatever you like. Okay, so this thing right here, this is the vector equation of a line in R2. Okay, so in two-dimensional space, that's your vector equation of the line. R is equal to R0 plus some scalar multiple of M. If I wanted a point halfway between here and here, I would take half of M. If I wanted a point all the way down here, that means that my t value has to be negative. Right now, my m is going up and to the right. So if I want to go down and to the left along the line, then I have to tell this to be in the opposite direction. So I multiply it by a negative value, t negative. The further down you go, the more negative t gets. And likewise, the same would work in the positive direction. Okay, now that t, let me just indicate that here, that t is called a parameter. And we're going to see that more and more in this chapter. Okay, so again, it's just a constant. It's a constant value. Now, I have this vector equation of a line in R2. I can take this and break it down into its components, because after all, this is some xy value. R0 is some xy value, which I have one of them here. It can be any point on the line. That's just one example. And I have my vector m. So what I'm going to say is, let R be some vector xy. R0 is going to be some vector x0, y0. Again, you only need a point on the line. And m you can get from your slope, right? And it has components m1 and m2. So that's why another way that I can write the vector equation of a line is like this. I can just say that xy is equal to x0, comma, y0. These zeros are called naught, plus t m1, comma, m2. All right, so that is another way for you to demonstrate the vector equation of a line in R2. Okay, let me add one more thing to this equation before we move on to a formal example. All right, so once again, this xy here, this is the position vector to an unknown point on the line. So position vector to an unknown point on the line. Okay, x0, y0, that is the position vector to a known point on the line. And finally, the m1, m2, that is the direction vector parallel to the line. Or rather, I should say a direction vector parallel to the line. And so that means any scalar multiple of this can also work. Okay, I'm hoping that makes sense and why it's clear now that you can have infinitely many vector equations, but there's only one unique scalar equation. Okay, let's try our first example. All right. Write a vector equation for the line through the points A, which is 1, 4, and B, which is 3, 1. My advice when you're starting out with these types of questions, always draw a picture. And those of you that take my physics class, you know that I always encourage that. Draw a picture. It'll help you understand the mechanics of the problem and help you avoid easily avoidable mistakes. Now, it's a good idea to start doing that in R2. So in 2 dimensions, I know I'm in 2 dimensions because I only have X and Y slots here, no Z slot. And then when you get to the 3rd dimension, you can use the analogies that you learned and understood well in R2 to then bring it into R3. Okay, so I'm going to just quickly do a sketch here. It doesn't have to be very formal, but it is a really good way of showing your work. Okay, so here's X, Y. Notice that I'm only drawing the first quadrant, excuse me, and that's because both my points are in the first quadrant. Okay, so I'm going to go from 1 to 4 on both axes. So there's 4, 2, 3, 1, 4, 2, 3, and 1. Okay, excuse me. So point A is 1, 4, so 1, 4. And point B is 3, 1, so 3, 1 is right here. Okay, now I want to know the vector equation for the line through those 2 points, so I need to draw a line through those 2 points. Okay, something like that. Now, usually what you're probably used to at this point is taking the points in the question and creating vectors out of them. Right? So you have to be careful. Just make sure that when you represent it as a vector, you know what it means and that you represent it using square brackets. So 1, 4, if I want to change that to a vector, I have to understand that the vector 1, 4 with the square brackets is the position vector going from the origin to point A. So that's this right here. Okay, so that's vector OA. The O stands for origin. So usually when you put 2 letters here, the letter on the left is where the vector starts and the letter on the right is where it terminates. Okay, so therefore OA is 1, 4. So let me just write that here. OA is 1, 4. And therefore I can state that OB right here is going to be 3, 1. Okay, so again, I'm trying to find a vector equation through that line. So I need 2 main elements for a vector equation. I need to know a point on the line, and I need to have some kind of direction vector for that line. And to figure out a direction vector for that line, well, I'm just going to try to figure something out based on the slope. Okay, so I'm going to call this the direction vector. I'm going to call this m. Again, your direction vector can be any scalar multiple of a vector that actually travels up or down this line. So I'm just going to let my direction vector extend from A to B. And I do that so that I can come up with a proper vector addition expression, which will allow me to determine the equation for the line. Okay, so step one, I know that my vector equation looks something like this. Okay, so always understand what your final answer has to look like, what form it's going to be in. It's going to be r is equal to r naught plus tm. Okay, so what that means is I have some x comma y value, which is equal to some x naught comma y naught plus t m1 comma m2. All right, so let's try to figure out what my m vector is, my direction vector. So in order to figure out what my direction vector is, I have to actually come up with some vector addition statement rather. So I know that if I have vectors lined up tip to tail, I can come up with a vector addition expression. So notice that OA and AB, so okay, I'm introducing a new thing here. What is AB? AB is M, what I'm defining to be M here. Right? The vector M goes from point A to point B. You could have had M go from B to A, that's fine, in which case your problem might look a little different, but mostly stay the same. So again, M is going from A to B, that's AB. So I can see that OA plus AB, right, is equal to OB. Okay, so that should be clear based on the rules of vector addition. Okay, so, all right, so let's do that. OA plus M, which I've called AB, is equal to OB. Hopefully that makes sense. And so if I rearrange that for M, because remember I'm trying to isolate for M is equal to OB minus OA. Okay, so OB is a vector, OA is a vector, and they're right here. So OB is 3, 1, OA is 1, 4. You know how to subtract these vectors. 3 minus 1 is 2. 1 minus 4 is -3. So 2, -3, that's a direction vector for the line. Now, the only other piece you need is a point on the line. And I already know 2 points on that line, so you can pick A or B. So 1, 4 or 3, 1. And of course, it's not the point that we put in, it's the position vector to that known point. So just make sure that you put the square brackets around that. So that means that my final answer, and I'm just going to try to squeeze it in here on this sheet. So therefore, there's 2 possible ones that I've come up with so far. And of course, if you did your M the other direction, you would have 2 other ones. So the first thing I need is a position vector, right? So I need to get to the line. So I can use either 1, 4, or I can use 3, 1, plus some scalar multiple times the direction vector. And that'll help me move up and down the line. And the direction vector is right here, 2, -3. Okay, so those are my 2 possible answers based on what I've arrived at here. So hopefully that is okay. By the way, I should mention that was part A of the problem. So let me just slide a part A in here. That's part A. We're going to move on to part B now. Okay. Part B, determine 3 more position vectors to points on the line. All right, so I already have 2 position vectors to points on the line, OA and OB. They go to points A and B respectively. So if I want 3 more position vectors, that means I'm trying to figure out 3 more vectors that go to various points on the line. Well, guess what? If I want to know the position vectors, that means essentially I'm trying to find 3 more points on the line. So i.e., find 3 more points. And then once you find the points, you stick those with square brackets, and they become the corresponding position vectors. Now, I know how to figure out any point on that line. I just came up with 2 different equations for it, and I can pick either one of them. Okay, so I'm going to go ahead and use the first one. So I'm going to use r is equal to 1 comma 4 plus t 2 comma negative 3. Now here's where we finally get to see that parameter in action. I'm going to try and figure out different points on the line. And if you remember earlier, I said that t is an element of the real numbers. It can be positive, it can be negative, decimal, fraction, whole number, whatever you want. Okay, so here I'm going to set different values for t. But to make my life easier, I'm just going to pick t values that are easy to work with. Okay, now just notice, I know it's usually tempting as the first value you plug in to be a 0, let's say. So if you plug in t is equal to 0, you're just going to get 1, 4, which is point A. So that doesn't really help you. Okay, let's try plugging in t is equal to 1. Some of you might already see where this is going, but let's just do it anyways. So that means I have r is equal to 1, 4 plus 1 times 2 comma negative 3. Notice I'm taking a scalar multiple of the direction vector. Well, if I do that, then that means I have, well, this is just going to become the vector 2, 3, or 2, negative 3 rather. So let's just write that in. So 1 comma 4 plus 2 comma negative 3. So we have 1 plus 2, which is 3, and then 4 minus 3, which is 1. Guess what? That's going to the point B. We already have that too, so that's not helping. All right. Let's try t is equal to 2. Now, it's not always going to be the case that t is equal to 1 gives you the other point. It just happened to be in this case. Let's try t is equal to 2. r is equal to 1 comma 4 plus 2 times 2 comma negative 3. All right, so that's 1 comma 4 plus 4 comma negative 6. So that's 1 and 4, which is 5, 4 minus 6, which is negative 2. All right, so 5 comma negative 2. That's another vector. And you know what? Let's call this R2 because this is going to point 2, just for our own sake. All right, so here's one more position vector. Let's try t is equal to 3. Okay, so R, we'll just call that R3 is equal to 1, 4 plus 3, 2 comma negative 3. So 1, 4 plus, and this is going to be 6 minus 9, which is equal to, so let's see, 1 plus 6 is 7, 4 minus 9 is negative 5. Okay, so 7 comma negative 5, that's another one. We just need one more. So let's use t is equal to 4. So R4 is equal to 1, 4 plus 4 times 2 comma negative 3. So 1, 4 plus, what's that going to be? That's going to be 8 and minus 12. All right. So if we add those, 1 and 8 makes 9. 4 minus 12 is negative 8. So there's my third position vector. And make sure you understand that now that I have 3 more position vectors, I technically know 3 more points on the line. Just replace the square brackets with round brackets. Okay? All right. Part C. Determine if the point 2 comma 3 is on the line. Now, if you had the scalar equation, you would plug that in for x and see if you got y is equal to 3 or vice versa. It's similar here. So let's remember what the equation I have is. So I'm using this equation. It doesn't matter which one you use. It has to satisfy both. That's a plus t 2 comma negative 3. Remember that this r is just an x comma y. Right? So if I plug, I know that this point can be represented by the position vector 2, 3 in square brackets. So I'm going to plug that in here. So 2 comma 3 is equal to 1 comma 4 plus t 2 comma negative 3. I have to remind myself that what I have here are different dimensions. I have x and I have y. So I can I can make 2 equations from this. I can make an equation in the x direction and I can make an equation in the y direction. Okay, so for the x direction, I have 2 is equal to 1 plus t times 2. And in the y direction, I have 3 is equal to 4 plus t times negative 3. Okay, so 2 is equal to 1 plus 2t. And y, I have 3 is equal to 4 minus 3t. This is the idea. If my t values are the same, then that means that that point does exist on the line, because that would mean that whatever t value that I extract from here, if I plug it in here, so let's say I plug in t is equal to 2, I use that t value on both the x and the y dimensions to give me this point. So that means that if I work backwards and I have the point, they have to return to me the same t values. All right, so let's rearrange these and isolate for t. So far I can isolate x to be, let's see, 2 minus 1 is 1. 1 is equal to 2t, and that means that t is equal to 1/2. All right, 3 is equal to 4 minus 3t. 3 minus 4 is negative 1. Negative 1 is equal to negative 3t. And sure enough, that means t is equal to 1 over 3. Oh, so that is not the same. Since the t values are different, therefore 2, 3 is not on the line. Since the t values are different, therefore 2, 3 is not on the line. Okay. So let's keep going. I want to show you something. Okay, so notice that in this problem I separated the vector equation into its constituent parts, into its dimensions, x and y. So I want to just generalize that for a moment and show you something. If I have the equation xy is equal to x0 comma y0 plus t m1 comma m2, I know that I can break that up into two separate equations, one for x and one for y in general. So x is equal to x0 plus t m1, and y is equal to y0 plus t m2. These two equations separated like this are known as the parametric equations of a line in R2. So just as the value t is called a parameter, these are called the parametric equations of a line in R2. Okay, so if you're ever asked for a parametric equation, you just take the vector equation and split it into its constituent dimensions. Okay? Let's try our next example. Example 2. Consider the line L1. Usually the lines are given with a cursive L. Okay, so L1 is the following line, and it's given by the following parametric equations. So x is equal to 3 plus 2t, y is equal to negative 5 plus 4t. Part A of this question asks us to find the coordinates of 2 points on the line. All right, so I know how to do this. I know how to find the x and y coordinates, so I just have to plug in various values for t and make sure I plug in the same t value for x and y for a single point, and I'll have values. So I can start off by plugging in, let's say, t is equal to 0. So for t is equal to 0, the x coordinate of this point would be 3 plus 2 times 0. Okay, and so that's just going to be 3. And y would be negative 5 plus 4 times 0. So that's just negative 5. Okay, so therefore, 3 comma negative 5 is a point. Okay, so I'm going to now plug in t is equal to 1. So if I plug in t is equal to 1, I get x is equal to 3 plus 2 times 1. So that's 5. And for y, I have negative 5 plus 4 times 1. That's negative 5 plus 4, which is negative 1. So therefore, 5 comma negative 1 is a point. Again, I just want to repeat that I happen to be plugging in integers, and small integers at that. You don't have to do that. You can plug in decimals, but I think that would get more complicated. All right, so that's part A. Part B asks us to write a vector equation of the line. So if you remember my little tidbit from before, there's not much of a stretch going from vector to parametric, right? So this was our vector equation. Vector equation, typically you want to express with the R value. So something like this, right? Before you just break it down, typically when we say vector equation, we mean this, but you can replace that with this expression. That's fine. Okay. So write the vector equation of the line. I already know the parametric equations, so it's not going to be that big of a step. I'm just going to force it into the formula like so. So I know the vector equation is xy is equal to x naught comma y naught plus t m1 comma m2. And I already have the pieces here, so I'm just going to put those in. So x comma y is equal to 3 comma negative 5 plus t 2 comma 4. And that's it. I just took the values straight from the parametric side. Okay, hopefully that's all right. Now something that maybe is not as straightforward, but will be soon, C, write the scalar equation of the line. So remember, this is one of the first things we looked at. The scalar equation is either going to be in standard form or slope y-intercept form. It doesn't really matter which one you put here. In order to get the scalar equation, something that is unique about the scalar equation, so let me just bring this back here for a moment. The scalar equation, nowhere in either of these forms of the equations is there a parameter. The parameter only shows up once you start talking about the vector equation. So that means I need to somehow remove that parameter. I don't want the t. So what I'm going to do is take these original parametric equations. I'm going to solve for t because I know that for any x, y point on the line, those t values are equal to each other. So I'm just going to isolate for t in each equation and set them equal to each other. So for the first equation for x, I'm going to have x minus 3 is equal to 2t, which means x minus 3 divided by 2 is equal to t. And then for y, if I rearrange that, it's going to be y plus 5 is equal to 4t, and then divide by 4. Y plus 5 divided by 4 is equal to t. Set those equal to each other. So x minus 3 divided by 2 is equal to y plus 5 divided by 4. Okay, I'm going to, well, you know what? Let's just simplify this first. There we go. So I'm just going to stick a 2 in the denominator on the right and a 1 on the left. And now I'm going to cross multiply. Take the 2, multiply it to the numerator here. So we have 2 times x minus 3, and then the 1 would multiply here, which doesn't make a difference, y plus 5. Okay, so I'm going to expand the left side. So 2x minus 6, and I'm also going to bring that positive 5 over to the left. That's going to become minus 5 is equal to y. Negative 6 minus 5, that's negative 11. So I have 2x minus 11 is equal to y. So, I mean, I've decided to do it in slope y-intercept form. You could just as easily do it in standard form. That's completely fine. If you do it in standard form, expect to get the following answer: 2x minus y minus 11 equals 0. Okay, so a simple check. You might have even just left it or skipped some earlier steps to arrive at that version. Okay. The last part of this question is part D. Determine if L2 is parallel to L1. Okay, well, let's see what L2 is. L2 is given by the following parametric equations. X is equal to 1 plus 3t, y is equal to 8 plus 12t. Now, if you had two scalar equations of lines and you were asked if they're parallel, it would take you about half a second to figure it out. You would look at the slopes and you would see that the slopes are either the same or they're not. And if the slopes are the same, you have parallel lines. And if they're not parallel. The slopes would either be the same or they can even be well, of course, the slope has to be the same. What am I saying? For scalar lines. For vector equations of lines, you've got direction vectors. So here for L2, my direction vector would be 3, 12. So M2 is 3, 12, whereas my direction vector for the first one is going to be 2, 4. Oh, let me just bring it up a little bit more. Sorry, 2, 4. Now with vector equations, they don't have to be necessarily the same. And in fact, it's rare that it's going to be the same. But what you know is that they can even be scalar multiples of each other. So for example, if I had two scalar slopes and one slope was 8 over 4 and the other slope was 4 over 2, well, 8 divided by 4 is 2 and 4 divided by 2 is 2. They're not written the same, but they both represent the same thing. Even if you have a rise of 8 and a run of 4, that's equivalent to a rise of 4 excuse me, and a run of 2. Okay, so likewise, you have to see if these rises and runs are the same. Okay, so in other words, you have to see if M1 and M2 are scalar multiples of each other. Okay, so well, let's see if they are scalar multiples of each other. If you look at it, they're clearly not. Okay, so remember that for your direction vector is given by x and y coordinates. Right? So the y coordinate is your rise and your x coordinate is your run. So this is another way you can look at it. You could look at the slope of line 2, so we can just call that M2 actually without the vector symbol on top. So we have the rise, which is 12, and we have the run, which is 3, right? Rise over run. 12 divided by 3 is 4. And M1, okay, again, rise over run, so 4 over 2, that's 2. Okay, so 4 and 2 are not the same. The slopes are different, therefore they're not parallel. And again, another way you could see it is that they're not scalar multiples. To get from the y value of 12 to 4, you have to divide by 3. But if you divide 3 by 3, you don't get 2, you get 1. So you can also see it like that. So since the slopes are not the same, or you could see it from this point of view, or M1 does not equal to a scalar multiple of M2, where k is an element of the real numbers. Therefore, L2 is not parallel to L1. Okay. Hopefully that's all right. We are officially halfway through the lesson. All right, let's move on to example 3. All right, example 3. Consider the line with the scalar equation four x plus 5y plus 20 equals to 0. Okay, so part A asks us to graph the line. Now, if you had it in y is equal to mx plus b form, this would be really fast. You could simply find the y-intercept, get the slope, done. Another way to graph a line that is pretty fast is to find the x and y-intercepts and then just draw a straight line through those. So I'm going to do that. I'm going to find the x-intercept. Okay, so the x-intercept we always find by setting y is equal to 0. And then I'm going to find the y-intercept, which I do by setting x equal to 0 and connect them, plot them, and then connect them with a line. All right, x-intercept. So here we go. I'm going to set y equal to 0. So that means I have 4x plus 5 times 0 plus 20 equals to 0. And then for setting x equal to 0, that's going to be 4 times 0 plus 5y plus 20 equals to 0. So let's just solve for the respective x and y quantities. So that's gone, that's gone. So 4x plus 20 equals 0. So 4x is equal to negative 20. X is equal to negative 5. Okay, on the right, 5y is going to be equal to negative 20. So y is equal to negative 20 divided by 5. That's negative 4. Okay, negative x and y intercepts. So that means I'm dealing with quadrant number 3. All right, so I'm going to produce my sketch here. And I'm going to be referring back to this graph. The reason why this question gets you to graph it in the first place is because it becomes so important to have these graphs, like I said earlier too, in order for you to understand visually what's happening in the problem. So based on these x and y intercepts, I'm going to have a scale of -6 to 6 on both axes. So I'm going to call that -6. So that's -2, -4, -2, -4, -6. Okay. And let's just stick the points in between that too. All right. So point A is the point, well, the x-intercept. So 0, -5, or sorry, -5, 0. So I'll call that point A. Point B, so let's just write that here, -5, 0. And point B is going to be the y-intercept, which is 0, -4. Okay, so I have drawn the graph. Here are the 2 points. I'm going to put the line through them. Okay, there we go, something like that. All right. Now, a couple things I want to point out. Since I've decided to call the x-intercept A, I can go ahead and call the vector going from the origin to point A, OA. So this vector is OA, and the vector going from the origin down to point B is OB. And kind of like I had earlier, I'm going to call this region in between points A and B M. Okay. Again, you don't have to draw it from A to B. You can draw it the other way around. That's completely up to you. Okay, so the first thing I'm going to do is come up with an expression that is, well, relating OA, M, and OB. I think this is going to be very helpful to us. Okay, when I add vectors, I add them tip to tail. So if I have OA and I add M, I'm going to get OB. So I'm going to write this out right from the start, just so I know that in case I need this later on, it'll become helpful. OA plus M is equal to OB. And M, because it's connecting points A and B, I can just call that AB. So OA plus AB is equal to OB. All right, let's go ahead and move on to part B of the problem so that we can see where we can apply this kind of expression. All right. We're going to keep coming back to this graph because it's going to be very useful for us. So part B, determine a position vector that is perpendicular to the line. Now, when I see the word perpendicular, the first thing that I always think of is that means that there's a dot product between two vectors that equals 0. Okay, so that means that if I have a position vector perpendicular to that line, well, there's the line. So that means that my the position vector perpendicular to the line is either coming out like this or it's going in the other direction, because that would still be perpendicular to the line. So whatever I have as that vector, it has to be having a dot product of 0 with the vector that travels along the line, which is M. M travels along the line, so I have to figure out what M is. Now, I kind of started that earlier. Let me just rewrite that in black here. I started that earlier, so I stated that OA plus AB is equal to OB. AB is the slope M. Right, that's the direction vector. I have to isolate for the direction vector. So if I isolate for M, I'm going to have OB minus OA. Again, this should look familiar from a previous example. Okay, so OB, okay, so that is the position vector going to point B. OA is the position vector going to point A. And I have the points. Remember, they're right here. -5, 0, and 0, -4. So I have OB, which is 0, -4, minus OA, -5, 0. And I get, let's see, 0 minus -5, that's 0 plus 5, which is 5. And I have -4 minus 0, so that's just -4. Okay, so that is my slope. Let's find a position vector that is perpendicular to this. So if it's perpendicular, that means therefore the dot product between two perpendicular, I'm just putting that symbol for perpendicular, two perpendicular vectors is equal to 0. All right. Now, whatever vector it is, whatever that position vector is, I know it's going to have coordinates x comma y. Okay, so if I take the dot product of that with 5 comma negative 4, I set that equal to 0, I'm going to get my position vector, or at least an expression that I can use to get my position vector. Now, if you're looking at that and saying, well, I have too many unknowns there. Well, you're kind of right, but it doesn't matter how many unknowns there are in this case, because the question is asking for a position vector, not the position vector. That means there's multiple answers here. Right, just as I said, you can have a position vector coming in this direction or going in this direction. It can be any length that you want. And so there's technically infinitely many answers here. All right, so if I break this down, I'm going to have 5x minus 4y is equal to 0. So 5x is equal to 4y. So, I mean, really what you need here is you need an xy pair that makes the left side equal to the right side. Don't pick 0, 0, because that vector has no length. And if a vector has no length, it cannot be perpendicular to this. So I'm going to just pick, well, if I put 4 for x and 5 for y, if I just switch the numbers around, that'll make the left side equal the right side. So that means that my m that I can use here, why don't we call this m star? M star is going to be 4 comma 5, right? So if I plug in 4 for x and 5 for y, it's going to make left side equal right side. So this is a position vector that is perpendicular to the line. Okay, I want you to take a look at those two for a moment. What you learned back in the day is that if you have two scalar equations of lines, they are perpendicular when the slope of one line is the negative reciprocal of the other. Now take a look at this for a moment. You have 5 comma negative 4. Remember that the 5 represents the x and the negative 4 represents the y. And so when you represent this just as a scalar slope, you have y over x, which is rise over 1. That's negative 4 over 5. Well, what's the negative reciprocal of negative 4 over 5? It's 5 over 4, right? You take the negative and you flip it. So if I take this, here's my x and here's my y. If I represent the slope of this m star, I have rise over 1, which is 5 over 4. And sure enough, those two things are the negative reciprocals of each other. So there's a few different ways you can do it. If you find it out using the slope first, you can then change it into the vector form. If you find out the vector form, you can change it into the slope form. Okay? Now, part C. Part C, I was just going to ask how the position vector from part B compares to the scalar equation. And so essentially what I just wanted to show you was that if you have y is equal to negative 4 over 5x plus b, let's say you have a straight line with this slope, you can get the direction vector for that vector equation of the line simply by taking the x and y coordinates and placing them in their correct dimensional locations inside the vector. We're not going to spend too much time with part C because I've already discussed it in part B. Part D, write a vector equation of the line. Okay, well, vector equation has two components. I have to get to the line, so that's r0, plus I have to be able to move along the line. That's the direction vector. Now, do I have a point on the line? Yes, I have 2 points that I've been given on, well, that I figured out on the line. I have A and B, negative 5, 0, and 0, comma, negative 4. It's up to you which one you want to use. I'm going to go ahead and use 0, comma, negative 4. So therefore, a vector equation for the line is 0, comma, negative 4 plus t times m. Now, my direction vector, remember, this is the direction vector along the line. This was the direction vector that we figured out that's perpendicular. You don't want to plug that in. You want to stick this one. Okay, so plus t times 5, comma, negative 4. And why don't we just put this in here? T is an element of the real numbers. So this is a vector equation of the line. Okay. Okay, and the next thing I want to show you is a bit of theory here. If I have a line L, and what's going to become more and more important throughout this chapter is being able to determine something called the normal to the line. Normal means perpendicular. So how do I find n? How do I find an expression for n directly from the scalar equation for the line? Ax plus by plus c is equal to 0. All right, if I have the scalar equation of a line, I'm going to try to get this into the form y equals mx plus b. Okay, so I'm going to get b by itself, so by is equal to negative ax minus c. Divide both sides by b, so y is equal to negative a over b, x minus c over b. And so what I can see here is I have y is equal to mx plus b. So my m is negative a over b. That's the slope of line L. Now, if that's the slope, that means that the slope of n, which is perpendicular, would be the negative reciprocal. So therefore, the slope of n is the negative reciprocal. What's the negative reciprocal of negative a over b? Well, if I multiply that by negative 1, I get a over b. And if I flip that, I get b over a. Right? So b over a. Now take that. I know that the b on top, that represents the rise, that's the y, and the a on the bottom, that's the x or the run. When I represent this as a vector, okay, so the direction vector for n, well, the y is b, and the x is a comma b. Those are exactly the coefficients of x and y in the original scalar equation of a line. And so what that tells us, and usually we don't call this m subscript n, we just call this n. This is an equation. This is a vector that is normal to the line, a comma b, the coefficients of the x and y quantities in the scalar equation of the line. Okay? That's a very, very interesting conclusion, and we're going to be using that idea more and more. All right. Before we get to our last example, I just want to go through a little bit more theory. I'm going to show you some comparisons between what's going on in R2 and in R3. Okay, in R2, if I have the equation ax plus by plus c is equal to 0, really what I'm giving you here is the equation of a line, the scalar equation of a line. Right, and if I wanted the vector equation of the line, so let me just go up here. There we go. If I wanted the vector equation of the line, it would be r is equal to r0 plus tm, or xy is equal to x0, y0 plus t m1 comma m2. T is an element of the real numbers. Those two are vector equations of the line. Now I took it one step further and I said, well, if you take those x and y quantities and you break them down into their component pieces, x and y, then you get what's called the parametric equations. So x is equal to x0 plus tm1, y is equal to y0 plus tm2, where t is an element of the real numbers. Again, these are the parametric equations. Now, a lot of time there's so much symmetry between what goes on in R2 and R3, and adding one more dimension simply makes something go from R2 to R3. Oh, you got to be a little bit careful here, okay? If I have ax plus by plus c is equal to 0 as the scalar equation of a line in R2, if I was to say, okay, well, what if I have ax plus by plus cz plus d is equal to 0? That is not the scalar equation of a line in R3. There is no scalar equation of a line in R3, okay? In R3, if I have this equation, this is actually what's called the scalar equation of a plane. A plane is a two-dimensional flat surface. And like I said, there is no scalar equation of a line in R3. Okay, so if you're working in the third dimension and you want to express the equation of a line, you need to express it using vector equation or parametric equation. So you can have r is equal to r0 plus tm. So this initial statement looks the same, but then you just have to remember that instead of x, y, you have x, y, z. So x comma y comma z is equal to x naught comma y naught comma z naught plus t times m1 comma m2 comma m3. Same deal, t is an element of the real numbers. Okay, so those are the vector equations of a line in R3. Likewise, you can take that vector equation and split it into its constituent parts and get the parametric equations, so x, y, and z. So x is equal to x0 plus tm1, y is equal to y0 plus tm2, and z is equal to z0 plus tm3. T is an element of the real numbers. Being able to break this stuff up into parametric equations is going to become paramount of importance for us when we start doing other sections in this chapter. Okay, we're going to go ahead and move on to our last example, which actually I think we can start on this page. Okay, example 4. Excuse me. A line passes through points A, 2, minus 1, 5, and B, 3, 6, minus 4. This should look very similar to the questions you've already done, except now we're in the third dimension, so the second. Part A, write a vector equation of the line. Okay, so vector equation, I know how that's going to look. I need a position vector, I need to get to the line, and I need a direction vector that moves along the line. Now, I'm not going to draw this out because this is an R3. This is what I said in the beginning. Get used to drawing out the pictures for R2 so that once you get to R3, you visually understand in your head how this geometrically works out. When you're in R2, we did an example, example 3, part B. If you want to see example 3, part B, we did this already. We figured out how to find the direction vector along the line, and we ended up determining that the M was OB minus OA. Okay. OB is just the position vector that goes to point B. So 3, 6, negative 4, minus 2, negative 1, 5. Okay, so subtract the constituent parts. 3 minus 2 is 1. 6 minus negative 1 is 6 plus 1, which is 7. And negative 4 minus 5, that's negative 9. So there's my direction vector. The only other piece I need is a point on the line, so I can get a direction vector to that point. And I know 2 points on the line, so you can pick either one of these. I'm going to go ahead and pick point A, but it doesn't really matter which one you pick. So R is equal to 2, negative 1, 5, plus T times 1, 7, negative 9. T is an element of the real numbers. And so again, the question says write a vector equation of the line, not write the vector equation. So there are many correct answers here, although there are still incorrect answers. So be careful when you're answering these. Okay. All right, so that's part A. Part B asks us to write the parametric equations for the line. This is the easy part. Once you have the vector equation, the parametric equation just falls out of that. You know that the R here is really some vector. It has x, y, and z components in R3. And so really what I have is x comma y comma z is equal to, and directly from here, 2, negative 1, 5 plus t, 1, 7, negative 9. I just break that up into its constituent dimensions. So I have x, y, z. X is equal to 2 plus t. Y is equal to negative 1 plus 7. And plus 7t. And z is equal to 5 minus 9t. If you're wondering what the point is of doing parametric equations, this is going to be of paramount importance to us when we figure out how to determine the intersection of lines. in R3, even R2, and also then the intersection of lines with planes, and eventually the intersection of planes with other planes. This is where Chapter 8 is headed. Part C. Determine if point C, which is given by 0, -15, 9, lies on the line. Okay, just like before, if you have a point on the line, then I know that a position vector going to that point can be represented with the same coordinates just inside of square brackets. So if this is a vector that goes to this line, then that means that the t values all have to be the same if I were to plug in these respective x, y, and z values into the dimensions in the parametric equations. We did this example in the beginning of the lesson, actually. Okay, so let's go ahead and solve for the t values. So going from the equation in the x is equal to 2 plus t, so that means t is equal to x minus 2. In the y is equal to -1 plus 7t. So if I rearrange for t, I'm going to have y plus 1 divided by 7. And then for the z, I have, let's see, let's just write this first. Z is equal to 5 minus 9t. So z minus 5 divided by -9 is equal to t. Those t values have to be the same. So I'm going to plug in these respective x, y, and z values into x, y, and z in these equations. And I should get the same t value, hopefully. So t is equal to x minus 2. That's 0 minus 2, which is -2. That's my first t value. If I plug in -15, I'm going to have -15 plus 1 divided by 7 is t. -15 and 1 is -14. -14 divided by 7 is -2. So far they're the same. You still have to check the last one, because if these two match and the last one doesn't, it's not on the line. If they all match, then you're good to go. Okay, z is equal to 9. 9 minus 5 over -9 is equal to t. 9 minus 5 is 4. And so then you have 4 over -9, where you have t is equal to -4/9. Okay, the t values are not the same. So we say that since the t values do not match for each dimension, therefore point C is not on the line. Okay, so that is our final answer. All right, well, that marks the end of lesson 8.1, equations of lines in R2 and R3. Stay tuned next time for lesson 8.2.